Hello, everybody. Welcome to the Dusk demo on the full release of our PLONK library. This is going to be a follow-on PowerPoint with some of the points of last week. We're just going to discuss about the reasoning behind our use of PLONK. We're going to talk about the types of use cases that we're going to have in the Dusk network. I'm going to show you guys how to build a circuit and then show you how the zero-knowledge stuff really works, and then give you a little parting gift at the end. So I am Luke Pearson, and this is the release of PLONK for Dusk Network. As you know, PLONK is a zero-knowledge proving scheme, and for us, it's the Rust implementation of the PLONK protocol, providing zero-knowledge proofs from a wide variety of computations. But that itself is all about the snark. So a bit of background, zero-knowledge proof systems, I think it's always easy every single time you do one of these, just to go over the essence and just repeat, or it's always, should we say, some paraphrase of a definition, because there's a few different ways to say it, but a system capable of cryptographically verifying a computation without revealing the solution. So that's the zero-knowledge proof system. And the zero-knowledge proof system we're using is PLONK. So this is a zero-knowledge proof system deployed in the Dusk network protocol, belongs to a family of zero-knowledge succinct non-interactive arguments of knowledge, or as you guys will better know them, snarks. They are proof systems, and this particular one is universal. It's got a universal and updatable reference string, so that's the, just saying a bit, the public parameters, or that particular trusted setup everyone talks about. In this next slide, I'm going to talk about PLONK. I'm also going to talk about the essence of the snark itself and what that does, and then you sort of sprinkle on a little bit of zero knowledge at the end. So for us, it's bulletproof, or it's snarks. We sort of make that dissection, and it's bulletproof snarks. And because we want to allow these large proofs, we end up choosing snarks. On a personal basis, once you do pick snarks, it's kind of a no-brainer for what we want to do for scalability and for these huge transaction bases that are going on the blockchain for big records. It's PLONK for me, because they're like, as you'll see in the abstract of the paper produced, it's like an advancement on the Sonic protocol. It does sort of all the same things, but it has shorter proof times. You'll see on the next bit, the snark computation, it's fail-safe. So it means that falsifying a proof means that every single person has to be malicious, or flipped on its head in a nicer way. In order to verify a proof, only one party needs to be honest. And this is based on testable and tested cryptographic properties. It's blockchain friendly. So blockchains, as you know, will scale much better if they only need to verify a proof and not compute it. The thing about snarks is that verification time is always almost constant, or near constant, 0.1. So when you have a program, let's say you have a program that runs for n cycles, then as n increases in terms of creating a proof each time on its cycle on a computer program, then verification of that is exponentially faster than computation. So that's about a snark itself, not with zero knowledge, but taking a computer program and being able to verify it really quickly. And then on top of that, we're able to verify it in zero knowledge using things like the computational binding and the homomorphic encryptments and the pairing curves. Remember, you've got the snark, you've got this ability to verify computations, and then you can do that in zero knowledge. So the next slide is just about how efficient we're talking our PLONK is. Well, the first is there's this trustable setup, which is updatable and universal. So what that means is there's one single trusted setup for the whole scheme, after which you can use the scheme with any program. It also means that there's a way for multiple parties to participate in the trusted setup, such as I said, that it's secure, only one needs to be honest. It's just sequential, so one's done without knowing the second or the third, and then they add on later, making it really easy and super safe in practice. And then we've got our proving times. So we've got our proving times O log n with respect to the number of gates, and then our fancy snark size here is the verification times. It's basically constant, and the same with the proof size gates. So we've got a super quick verification on the blockchain there. And the principal points of PLONK, this is just a quick recap from the first installment. Versatility, it can be used for anybody, and it can be used for any project you choose. And the ease of use, I think this is something we really try to hammer home as a team at Dusk. it's very, very important for as many people to understand and be able to interact and begin to adopt this technology without needing, a computer science degree, or without needing months of practice to be able to understand. And for that reason, we document really, really intensively in our library every decision we feel that needs something. But we would like people to be able to roam through this library and understand, and help them understand the workings of Rust and help them understand this new, novel, awesome technology. We've also done the library a lot of optimized circuit construction. So we build a variety of circuits. We've got a variety of gates, and we've got custom gates on top of the addition, multiplication gates, and there's no restriction on the amount users can build. And then for security, we use the BLS 12381 curve, and it's proven to provide high level security. So next, this is the essence of it all. This is how you compose, you construct, you build your circuits. So you have a computer program, and it's got just a sequences of additions and multiplications and binaries and Boolean gates, and even some sneaky little custom gates in there. You've got your elliptic curve cryptography. You take all those operations and you construct a circuit out of them so it can be correctly evaluated and turned into a zk-snark. And this is what you're going to be using when you're using our implementation of PLONK. So alongside these standard addition and multiplication gates, we've got custom gates. So custom gates like the elliptic curve, or the ECC gate, just shorten it down there for you. It would allow your computer programs which have these ECC to run them through without having to diverge into other operations, and you can save so many constraints on that. We've also going to have exponentiation gates, so you have to the powers of 2 for these numbers. We're even thinking about really specific gates, about raising things to the power of 5. And basically, it's just all these computer operations have all these different ways of finding the result. And we need to be able to do it such that people can get that and port it into a Dusk PLONK circuit. And then they'll be able to sprinkle some of that zero knowledge right across the top. For this, as one of the things I spoke about before, the API. The API is built in. It's got sets of examples of how to build these circuits, and even within the modules themselves, there's documentations, and I'll take you all through that in about 5 minutes. We're able to, onto the third point, enhance this variety of circuits. So circuits where you're controlling the size, because you're selecting the size and number of gates, the selector polynomials, it's all in your power. You can make them large. There's no restriction on these gates, no restriction on the shape of the circuit. You construct it how you want, and then based on your computer program, and then you run it through, make it on zero knowledge, and you've got an independent, perfectly controlled constructed circuit with the TurboComposer from our implementation. And the reason this works so well is because when the dependency of PLONK is using a Rust project, there'll be no clash. You won't have to refactor it for every API change. You'll just be able to port it, create a dependency, and bam, build your circuit. Building a proof. So I'm going to take you through the steps of how you build the essence of a zk-snark proof, and then I'll show you how to, well, I'll show it in tangents with something in our library in PLONK. So for that, so if you just fork or clone the library, you come to this file here, examples. So I'm going to show you guys all how to build a proof. We picked one here, but what I'll do is I'll take the window on the left. So I'll show you how the examples folder is working, and then I link it to each of these steps going down the right. So maybe, if we keep them up, there's some decent tangibility. So we're going to be using the trusted setup here, which is standardly taken a multi-party computation, and then it's created in this secure way. These public parameters, as you know, are shared between the verifier and the prover, their computation, so that they can encrypt the values and then keep them secret. We let them equal public parameters, and for also, I'll show you in a little bit this serialization and also deserialization process, for them to be reused. Okay, on to number 2, which is building the circuit. Remember, I'll be picking a specific circuit here and take you through it, but it's just any computer program where you want to prove that what you've stated, so the computation is actually equal to the solution without showing any of the values here of the computation. So you want to state that this is a solution without revealing anything other than the fact that you've said that. So circuit we're going to build for this sum right here. So this is saying that A plus B is exclusive OR C plus D. So we've got on the left side, I always think of it like this. If you see the standard sort of arithmetic circuit construction, on the left side, you've got A plus B going into a gate. On the right side, you've got C plus D going into a gate. And then the outputs of them both go into a gate, which is an exclusive OR gate, so that either one or the other is in fact equal to 1. And you have this public input of 1, and then the reason we chose this is you can check the public input. You can also check that the output is Boolean. So that means in the range of 0 or 1. So it's yet to show another gate that we have. So moving on, when you input these A's, B's, and C's and D's, we let them equal scalar. However, for an add input, we need to take this scalar and turn it into a variable, because then you can be using inside of the circuit, because these are your secrets, or also known as your witnesses. And you've got these value set. You've got secret values set for A, B, C, and D. And then first, in this constructing the circuit, you're sort of sticking with the mental image I hope I've painted. We're computing the left side, which is A plus B. And then you want to compute the result and get it as the output wire. So that'll be ready to go to the XOR. And then we'll do the same with the right side, which is C plus D, and then we'll get it to go to the next gate. So we take this function, just the add function, with the width here being standard, unlike in the next example that I'll show. The constants that we have are set to 0, the public inputs are set to 0. So we have this, this Q1 being the selector for the left wire, equaling just 1 times what A is set to, which is the variable. And then we have the same with B, where B is set to the variable here, using our add input function. And remember, you can always command or whatever it is on non-max and I think it's control and click and just go to these wherever defined and have a little play around with the library. So we've got our A plus B. We've now got to do the same thing with our C plus D. But just to show you something a little bit different, we've gone this with our big add. So rather than width 3, which as I said, I'd called it standard width here, but we just say width 3 because it's fan in 2. There's two values in, 1 value out. So 2 wires in, 1 wire out. We're using our width 4. In this case, because it's still the same, we set it to 0. But it's just showing that you can, in fact, as I said, in line with the whole control over the shape of the circuit and the prescription of it is in your power, you can, in fact, have the different widths here. And now you've got these 2 outputs. So you've got, remember, the A and the B going in, which gives you A plus B. And then you've got the C and the D coming in, which gives C plus D. And now you need to do an exclusive OR on these results. So you just call on this logic exclusive OR gate, you create the inputs, and then this time, we've selected the size. You can always use the largest size, but it's quicker not to have excess of bits. So in this side, we pick 10U size because we know we'll never have more than 8. But if you're not too au fait with how that works, then you just use the standard, as it says here, 254 bits. And then the other thing we're doing is we're checking that the input is in the range 0 to 1 with this bool gate. So just taking this declared AB XOR CD into here, and then we constrain it to a constant. Then we were able to perform that subtraction. And then we're doing the whole aggregate with it all, which is similar to what's been done before, but we just have different values based on the formulas that are written out. It's written here, but it also will be higher up. And then we're selecting different values for this with constants and with well, still 0 in the public input, but with now the wires sticking to that value. So that's 2, that's most of 2. And then now we want to be pre-processing the circuit. Now that we've got these AND gates with our values. And the pre-processed circuit is just pre-processing what would come out of this circuit that you've created. We have to have these transcripts. And in this example, we've shown that the transcript that allows us to have this Fiat-Shamir heuristic is separate for the prove and verify, but it's in fact the same. It's not separate. We just created 2 so that you can show that they in fact both need one, but they usually just share one across them. So we have these public parameters taken for which, so before we've serialized, and then the pre-processed circuit, we have the pre-processed prover key, the prover transcript, and the evaluation domain from the prover transcript in here in the evaluation domain, and the prover key being the public past the public parameters that I spoke about. And then moving on to step 4, you go to the proof and obviously just go to this function to see how what it takes, and then it just returns this proof from the committed key in the pre-processed circuit, the transcript, and we've got all of those in. And then you're able to verify the proof here with an assertion. Once again, you will need to go to this function to see what you're taking in, and we're taking in the pre-processed circuit, the protocol, and the verifier key. That's from the same, well, would be from the same set of transcripts. And moving on past this, we've gone through the 5 steps. So it mostly permeates this 0 and 1. We're just going to show you some of the slightly more advanced stuff in PLONK, which is the gadgets. So one of the things we don't want to be doing is creating a circuit every single time. So we're able to reuse created circuits. So there are lots of gadgets to go through this. I won't take you through them all because it's quite a lot, but feel free to have a read through. And then if there are any questions, open issues, send an email. I will always answer. Going through, it's sort of the same for different gadgets here. The different gadgets, different things allow you to swap and change the values from what's been stored before. And then builds the pre-processed circuit quickly in one function. I think it's let build prep circ. But the one thing I do want to show you at the end is that just this quickly, and it's the lazy static. So the lazy static, I was talking about the ability to call back a reference to circuits created before, and then with the evaluation domain, which also the pre-process itself has the transcripts inside, and then the keys from the verifier and the prover that have been shared, and then just reusing them with different values, so you don't have to keep recreating this stuff. So just to get some context for those who are less techy, I'll speak about some of the use cases of PLONK as snarks in general, and then I'll actually show you some of the cases within Dusk. The first, of course, is these private transactions. There's no linkability. Is that when a transaction's sent, a sender's address, a sender's input value, as well as a receiver's address, and the output value are hidden. And they're often called, I think we'll call them shielded transfers. All that has to happen is that the sender proves that they have the private spending keys of the inputs, and then that gives them the authority to spend, and they prove this in zero knowledge without disclosing any information about themselves. The other one is the de-anonymity, which is just that you don't know those who are spending these notes, and all they are is cryptographically linked to like a signature based on the entire transaction per party. And they're done in such a way that this transaction can't be modified by anyone who, for example, didn't know the private keys. So you have to know the private keys. One of the things that we're going to be using it for in PLONK is the blind bid proof. So just as a little recap, the blind bid proof is what allows Dusk to have a private proof of stake protocol. So the proofs utilize this extraction of the round leader for the consensus from a set of block generators, and they do all of this without revealing the identity of the person or the amount of Dusk that they have staked. So you're obfuscating these stakes. And then the proof proves the inclusion of the bid in a set of all Merkle tree bids. So this is part of the ensuring the correctness. But how it works is the knowledge of the amount the block generator is privately staked and the correctness of the computed score is done, which again depends on the amount of stake. And just while I've been talking to you on this slide, I'm running a benchmark on my terminal on another slide to show you in line with something that in the Dusk network and in the Dusk code is already using PLONK, and it's Phoenix. It's our transaction layer. Phoenix uses Dusk when those people want to spend money to prove that they in fact have the balance. So they can't, in principle, spend imaginary money. You have to make this proof, and this proof is done in zero knowledge. And I will flick to that slide now. So as you can see here, we've got a verification time of almost bang on 6 milliseconds, which is awesome and just in line with what we said before. And then we have a verification time of 6.5 seconds, which is awesome again. So as you can see, the verification is much quicker than the proving for these gates, and that's why Snarks are efficient for verification on the blockchain. One of the parting gifts is if you want to contribute, this is the link you go to, even if you just want to raise an issue or you want to fork it, play it on your own, clone it, see how it works, go through those examples, and then feel free to amend things, improve things if you can, and maybe try and get yourselves a pull request in there. And then this is what is now, if you go to this link, you'll see that the crates.io has already been released for our version 0.1.0 of PLONK. And you've got everything you need here. And you'll be able to go through and have a look at the documentation, the repository, and yeah, have a little gander at this library. And download it, have a look at the crate, and this is of course where you can create the dependency as well for your own particular projects. This is where you can go through your issues. This is where you can go through, you can clone it. This is where you can fork it. You can have a look and then maybe dependence it into your crates. Please don't hesitate to ask if there are any questions. That is everything from me. Thank you all for joining. Thank you all for listening.